Hi guys, let's do shortest path in a grid with obstacles elimination. Also, I'm currently traveling right now, so bear with me with my current background, but yeah, so we're given an m by n integer matrix grid where each cell is either 0, which means it's empty, or 1, which means there's an obstacle there. We can either move up, down, left, or right from into an empty cell in one step. So basically, if we're starting in this cell, and we move one to the right and we're now in this cell, then that counts as one step. So they want us to return the minimum number of steps to walk from the upper left corner at cell 00 to the lower right corner, which has coordinates of m minus 1 and minus 1, given that you can eliminate at most k obstacles. So if it's not possible to find such a route, then return -1. So given example 1, we're given this grid, which is given to us in the format of this 2D array, and k equals 1. Then we can output 6. So basically, if we just find the shortest path without any obstacle eliminations, then starting from the top left corner here, we could take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps, right? But since we are given k equals 1, we're allowed to eliminate at least one obstacle. And so if we eliminate this one right here, then that would take us from 10 steps down to 1, 2, 3, 4, 5, 6. And so we could actually make it to the bottom right corner in 6 steps instead of 10. So we can return 6. And in example 2, we are given this grid, which is given to us in the format of this 2D array, k equals 1, and we output -1 because we would need to eliminate at least 2 obstacles to be able to actually make it at the bottom right corner. Because if we just eliminate this one, we cannot travel diagonally, so we're kind of blocked from either this one or this one. If we eliminate this one, then we're blocked by this one or this one because we can't get there from here. And if we block this one, then we're also stuck. So no matter what we do, we are stuck, and so we would return -1. So this one is actually very similar to that other problem that we did recently, the shortest path in binary matrix problem. Pretty much the only difference is that we have obstacles in this one, which we did not have in that problem. So we can store all of the directions in an array again. And basically, we are going to start from the very top left corner. That's going to be like the root of our, we're going to do a BFS from there. Because anytime we are looking for a shortest path, it's pretty much going to be BFS. And we are going to explore the neighbors by using our directions array, right? And the only difference really is that we're also going to have to keep track of the number of eliminations we have left as we go. So we just need to make sure that it's greater than or equal to 0 at all times, otherwise we don't have any left. And so we're going to have to explore all possibilities with that as well. And we will, so we know we're going to also actually, so we can't, we are going to want to no, what am I saying? We're going to want to have a visited array as well to keep track of each state in the grid. So I'm going to actually just assign m to grid.length and n to grid at 0.length, so for the rows and columns, so that we can access this instead of continuously calling these, just so it's a little bit more clear. And then also because they give it to us in these coordinates, in these variables, so we'll just continue with that. So our base case, if we're only given one cell, then we'll just return 0 because there's no steps to be taken. So if m is 1 and n is 1, return 0. Okay. Alright, and then we will set up our visited array. So Boolean, and we're going to make it 3D, this array, visited, and we're going to make it m, and so the same dimensions as the grid for rows and columns, okay? And then we're gonna do another one for k, but we're gonna make this k plus 1, because basically if k equals 0, then let me think about this. So if k equals, like, we want to make it 1 bigger than k, because if we're given k, then we have two possibilities here, right? K equals 0 or k equals 1. And so if we only make this k, then this would be of size 1, but we have two possible states there, which is 0 and 1. So we need k plus 1 basically to make it so that we can also include 0 as a possible state, if that makes sense. And then we're going to set up our queue for BFS. So this is going to be an int array, because we're going to store the coordinates in our queue for whatever, to represent whatever cell we're at. And then along with the coordinates, we'll also store the number of steps we've currently taken and how many eliminations we have left. So we'll just keep track of that information as we go. So queue is new linked list. All right. And now we can add our root into the queue. So we'll add 0, 0, and 0. Okay, because this is representing row 0, column 0, and we've taken 0 steps so far. And then we'll also add k, because that's the number of eliminations that we have left. And I'll label it here. So row, column, steps, and eliminations remaining. Okay. And then we will also assign this coordinate in visited to true. So that means we have visited this state already, which we now have because we added it to the queue. Okay. Then we will set up our directions array. So we'll have 1, 0, negative 1, 0, 0, 1, and 0, negative 1. And again, right, this is representing rows, this is representing columns for each one, row, column, so on. And positive for row, as if we look here, means we're going down. Negative for row means we are going up because the number is getting smaller. Positive column means moving right. Negative column means moving left, because we just follow the way the numbers are moving here. Okay. And then now we'll do our BFS. So while our queue is not empty, then we'll continue with BFS. So we will say the top cell is going to be the top cell in the queue. So currently our queue is storing this. And I guess if we look at example 1, then k equals 1. So we would have 1 here. Okay. And so now, but we just removed it from the queue. So this is gone. And it's now stored in cell. Okay. Then we can assign row to cell at 0, column to cell at 1, steps to cell at 2, and we'll just call it remaining for the number of eliminations left equals cell at 3. Okay, so this is column 0, or the row is 0, the column is 0, the steps are 0 so far, and the number of eliminations remaining is 1. Okay, now we want to loop through all of the neighbors of this cell. So if we're up here, we want to loop through this cell and this cell and check which one is we want to check if they're like legal options, right? Like we can actually go there. So like technically we can go either way currently, because our step count is still, not our step count, we still have an elimination left. So even though this is a 1, we could use our elimination and go this way, or we could not use our elimination yet and go this way. So both ways are valid so far, but we're going to loop through. So for each direction in directions, we are going to assign the new row to our current row plus direction at 0, because the 0th index is always the row, or the way we're moving in the row, I guess. And this will be column plus direction at 1. And then we need to check if it's in bounds. So if new row is greater than or equal to 0, and it is less than m, and new column is less than or equal to 0, and new column is greater than or equal to 0, and less than n, then we will so we'll take the number of eliminations left and we'll subtract the number here. So if we used it, then this will be a 1 and it'll be 0, and if we didn't use it, because this would be a 0, we'll still subtract 0, which will still give us the same number. So new remaining is the current remaining minus the that original, or no, the new cell. So this one or this one. So at new row at new column. Okay, and then basically we want to check that we can actually eliminate it, because like we don't want it to get into the negatives, because that would be bad, right, and not actually legal. So if it's new remaining is greater than or equal to 0, and we have not already visited this cell, then basically then we will check if we're at the last coordinate. So if we're at here, then we'll increment steps. So and then we'll return it. So like if we get to here and then that's 5 steps, then once we get here we'll just return 6, right? So otherwise we're not at the last step and we have more steps to go, then we will mark the current cell as visited. So new row, new column, new remaining is true. And then we're going to add it to the queue to be visited in the next iteration. And we need to increment steps either way, so. Sorry. Yeah, that's right. Okay, and then we're going to do this for the entire grid, and then we will, if we go through the entire grid and there's nothing, we will return -1. Okay. What did I do wrong here? This should be double 2D array. Jeez. Okay. There we go. Okay, so let's do another example. Like, let's say, so if we're at the top left, then we go 1 to the right and 1 down. So then we would add the new row is going to be 0, 1, and 1, 0, right? And the steps, so if we go to this one, 0, 1, then the steps are 1, and the eliminations remaining is 1. This one is going to be 1 step, and 0 eliminations remaining. So that would be what's in the queue after our first iteration, right? Because we would have added this, and visited will be true. So then when we remove this off of the top of the queue, then that goes there. This is removed. And for each direction in directions, our new row is our current row plus directions at 0. So 0 plus 1 is 1. So that becomes, our new coordinates will become 1. Our new column is current column plus direction at 1, which is 0. So this stays at 1. And then if it's greater than or equal to 0, it is, this is less than m, it is, this is greater than or equal to 0, it is, and this is less than n, which it is. Then new remaining is remaining, which is 1 minus the grid at new column. So our current remaining is 1. This is 1. 1 minus 1 is 0. That becomes a 0. And then if it is greater than or equal to 0, it is, and we have not visited that, then new row. So we're not at the bottom right yet, so we ignore that. And then we mark it as visited, and then we add this into the queue. So then this will get added into the queue like that. Okay. And then we basically do this for all directions though. So this is just one direction, so I could show you guys. Anyways, yeah, I'm not gonna go through all of it because that would probably literally take all night. But let's go over the big O now. So the time complexity for this one is O of, so let's think about what's going on here. So basically, okay, we are visiting every single cell, processing every single cell in here. Like worst case, we have no obstacles, or the number of obstacles that we can eliminate is the same as the number of obstacles we have. And so if that's the case, we're processing every single cell in the grid, which is m times n. But we can also visit it in with any possible remaining k left, right? So if k equals 0, so we have no obstacle eliminations, and we don't have any obstacles, then we're visiting m times n, right? But if we have k equals 1, and let's say like every single one is an obstacle, then we're visiting every single cell once like with k equals 1, and every single cell once with like k equals 0, because we need to compare the two to see which one is better. And so basically that will give us O of m times n times k, actually, if that makes sense. So yeah, and if we take a look at the code, so it's really just all in the BFS here. Because we're adding every single cell into the queue with k possibilities of, like, because, like, do you get what I'm saying? M is rows, n is columns. K is number of remaining eliminations. Yeah. Space. So let's think about the space. So our data structures here, God, if I can speak, are our visited array, which is like literally the same size as grid, except we also have another dimension for k. So that is actually already like O of m times n times k, because it is storing every m and n, but like also for every k. So that's already O of m times n, blah. O of m times n times k. And the q, we have this q here as well, will also store O of m times n times k in the worst case, because the q is storing everything we're doing in the BFS, and if we go back to like the time complexity from the BFS, it was already O of m times n times k. And so worst case, the q would store every single node, which is literally this. So let's see, the only other data structure here is the directions array, but that is constant because we only have 4 directions. And that is it. So basically the time complexity, the space complexity is the same. So that is it for this problem. I hope that was helpful. If it was, please like and subscribe, and I'll see you guys next time. Bye!